Hello. Hey, let's do a paper one. Just for fun, I'm making a little video solution to the paper one here, our specimen paper made special just for us for practicing for these new and exciting IB exams this year. I've kind of skimmed this, but I have not really gone through it, and so I want to kind of talk through my process as I do this too, of how I would like think through these questions. And I'm also keeping an eye on my time. This is the paper 1A, which is the multiple choice section. This is the HL one. It is 40 multiple choice questions for the whole paper one. They're doing it in this funky way where they just give you everything at once, the 1A and the 1B. 60 total marks. You have 2 hours. That's 2 minutes per mark. You may want to save a little extra time for the 1B because there's more writing and like drawing, lines on graphs and stuff. But in general, we're going to shoot for no more than 2 minutes per mark. So 80 minutes at the most is how long you want to spend on the paper 1A. If you can get away with a little less, great. So I'm going to try to keep an eye on my time and keep this to certainly under 80 minutes. Let's see how we do. Okay, let's just start with number 1. And I see here, I'm so happy the first problem on my first physics test is SUVAD. This looks a lot like SUVAD to me. I got a car with an initial speed decelerating until it stops, so it's the distance traveled by the car. I should make a quick sketch because it's SUVAD, and for basically any physics problem, I should make a sketch. It will help. All right, initial speed, 16 meters per second. I'm going to draw that like this. Initial speed, I know we're talking about u. It decelerates at 4 meters per second until it stops. Okay, it is not, this is going to be a negative acceleration. A equals -4 is what I'm going to do. It is not a negative acceleration because it's slowing down. Okay, and it's not negative because it's decelerating. You could do this problem, and I encourage you to try this problem, especially if you don't believe me. You could do it the exact opposite way. You could say we could say this thing is moving to the left, and we could say u is negative 16 meters per second, and a is positive 4 meters per second squared. The rule is if you're slowing down, your acceleration is in the opposite direction to your velocity. Negative acceleration does not mean slowing down, right? It just means you're changing your velocity in this direction. Okay, make sure you're okay with that. Anyway, let's go. We know it stops, so we know v equals 0, I think. So what else? What am I looking for? The distance traveled by the car. So I want to solve for displacement. Well, here I am in mechanics because I know our first couple problems are going to be about this. I want my trusty Vutas equation. Because I don't know anything about t, so let's pick, and I don't care about solving for t, let's pick the one without t. Okay, v is 0, so I can solve this for s. I'm going to subtract u squared from both sides, divide by 2a, so I think I get negative u squared over 2a. Vector, vector, vector. Okay, and let's plug in our numbers. So it's going to be negative 16 meters per second squared over 2 times 4 meters per second squared. Oh, sorry, negative 4 meters per second squared. Okay, 16 squared over 2 times 4. Oh, it's like 16 times 16, 8. What's this, 32? And I got a negative over a negative. I have a positive 32 meters. Or if I'm doing it this way, makes sense to me. If you do it this way, you would get negative 32 meters. In either case, we're saying the same thing. You move in the direction of your initial velocity, 32 meters. Okay, let's keep going. A block of mass 2 kilograms accelerates from a speed of 15 meters per second to a speed of 20 meters per second without changing its direction. What impulse acts on the block? Oh, what a gift. I know what impulse is. I know the definition of impulse is change in momentum. Well then, all I got to do, the mass doesn't change. M delta V works great for delta P if the M doesn't change. All I got to do, 2 kilograms times the change in velocity was 5 meters per second. It's 10. That's it. What a great problem. Let's keep going. A net force of 8 newtons accelerates a 4 kilogram body. I'm thinking we're doing this. Nope, just kidding. I should have kept reading. I want to know the work done by the force. Okay. The work done by a force, the equation for the work done by a force, I know is this equation because I studied my data booklet, and that's like what this equation is. So what do I need to know to solve this? I need to know the net force. Well, that I got. I need to know S, the displacement. Okay, maybe I will need this. Because I need to find displacement. What else do I know? I'm given M. I'm given the speed it gets up to. Also, it's accelerated from rest. Let's see. Do I have enough to suvat my way to success here? I think I do, because I can find A, right? I know the net force. So let's find A. Acceleration is going to be the net force divided by M. I'm remembering this is net force, but I'm okay because they're giving me the net force. So the acceleration is going to be 2 meters per second squared. So now I know V, U, and A, and I want to solve for S. Let's go back to my suvat equations. We're going to use the same one. They don't like giving us time right now. That's okay. We don't need it. Let's use this guy again. V squared equals U squared plus 2AS. Wow, we're using that kinematics equation again to solve for S? Really, IB? Okay. Let's do it. S is going to be, now U is 0, but it's going to be real darn similar. S is going to be V squared over 2A. V is 5 meters per second squared over 2 times my acceleration. So 25 over 4 is my displacement. Yeah, I guess so. Okay. So let's plug that in over here now, because remember what I'm trying to do is I'm trying to solve for work done by a force. I need Fs cosine theta. Okay, theta, remember, is your angle between F and S. If my thing is being pushed by some force and going some distance this way, almost always this angle is 0 degrees. The cosine of 0 degrees is 1. So I can just ignore this because it's just 1. So work is going to be the force, 25 over 4 newtons times, nope, sorry, that's my displacement. The force is the 8 newtons they gave me times the displacement of 25 over 4 meters. Okay, I see what we're doing now. That's 2. 2 times 25 is 50 joules. Okay, beautiful first 3 problems. Just some straight up mechanics stuff. Those are pretty nice. I do want to spend my time on those. I spent, I think, a little more than 2 minutes per mark here as I'm talking a lot too. But that's worth it. Like, these are very doable questions, so I should take my time and make sure I do them, make sure I write out all the math, make sure I'm not like thinking I can just like divide displacements and velocities and stuff to find what I need to do. I'm like fully using the suvat equations. Okay, let's keep going. Oh yeah, now we're doing some rotation. I'm immediately turning my data booklet to 8.4 because that's where I know all the rotation stuff is. They give me the equation here. I see it's a disk, and I know they're always going to do this because I don't have all the moment of inertia equations. They're going to have to always give it to me. So I know something's going to happen with I. Let's see what we're solving for. The angular acceleration of the disk given I. Seems pretty likely to me. I'm doing Newton's second law rotation wise. 2 equal and opposite forces, each of magnitude F, act on the disk. Okay, acceleration, forces, moment of inertia. I want to use the F equals ma of rotation. Torque equals I times alpha. And the torque, remember, this means the net torque, add up all the torques. I want to use the equation for a torque caused by a force. It's F times R times sine of theta. When you have your forces applied at right angles like this, remember that angle is the angle between like F and R. And very often that's 90. Sine of 90 degrees is 1. So in a lot of this like trig stuff, especially on a multiple choice, honestly, those turn into like a 1 or maybe a 0. So each of these forces causes a torque of F times R. There's 2 of them, so I think the net torque is going to be 2 times FR. That's the total torque happening. That's I alpha. I want alpha, so I'm just going to do divide both sides of this by the moment of inertia. I'm going to then take my moment of inertia equation and put it in there. So whole big mess for a second, 2FR over 1/2 mr squared. Let's try to not mess up fractions. 2 divided by 1/2 is 4F over mr. That's an option. That's D. D looks pretty good to me. I might even star this if I'm not feeling confident about my fraction math right there. But that seems pretty good. Let's move on. Oh, great, an elevator. A person standing in an elevator, aka a lift. The total mass of the person and the elevator is given. Given the acceleration, what's the tension in the cable? Okay, F equals ma is the equation to use here. If you just solve for F, you're doing it wrong. Like that's not the answer, because remember this is net force. So I need to think about all the forces happening. Tension is one of them. But of course, there's another force that I need to account for, which is, let's do this, which is the force due to gravity acting on everything. We're accelerating upwards, so be thinking about sizes of forces. Tension has to be bigger than gravity. Okay, so tension minus Fg equals ma. This is a classic problem where tension is the net force plus gravity. Tension's got to be bigger than gravity and bigger even than the net force, because tension is going to beat Fg. And when I do tension minus Fg, I end up with however much this is. Okay. All right. Now that I know, remember that like F means net force, I'm good to go. We're just going to plug in. I can save myself a second if I do this and go, okay, the mass is 800 kilograms times, no, 2 plus 10. Sorry, eraser. Okay, so the acceleration is 2 meters per second squared. Here on the multiple choice, you can usually get away with using 10 meters per second squared for G. That's good enough. So I want to do 800 times 12 is really what I want, which is 8,000 plus 1,600. That's going to be D. Yeah, so D will be the answer to this one. Remember that F and F equals ma is net force. Okay, number 6. We drop a thing in a vacuum, height h above Earth's surface. It's this point. What's the kinetic energy at this height versus the potential energy at this height? Yikes. Okay, this is like lots going on. I want to take my time here. Again, we're still on mechanics. Like, take your time on these first ones. Honestly, if you spend more than 2 minutes per mark on these, I think that is all good, because you can get these marks usually a lot easier than some of the later ones. Okay. So it starts h above the surface. I'm going to draw it like this. And let's think about both types of energy that's happening. The potential energy here would be mgh. Kinetic energy here, I'm thinking is 0. I'm also knowing how these problems work. Like, this is the total energy. So at any point, here, the total energy is this much. And it's just like, you know, at the bottom, all of that energy is kinetic. In the middle, maybe half and half. So I want the kinetic energy of the object at a height of 0.75 h. Well, here's how I'm kind of thinking of it, if this makes sense. At this point, the potential energy is 0.75 mgh, because really it's m times g times your height, right? And so like 70 you have 75% of your total energy. Here's potential, so I must have 0.25 mgh as kinetic. Yeah. Okay, so to do this fraction, I'm just trying to be careful with how I set up this fraction because it's kinetic over gravitational. The kinetic energy at 0.75 h is this much. So that fraction is going to be 0.25 mgh over potential energy at a height of h. That's just my total energy. Well, I'm thinking it's just B. Yeah, it's just a quarter. Okay, so sketch it out. Picture what's happening in terms of total energy. That seems to me like it's going to be 1/4. Okay, let's keep going. Okay. Now I've got another rotation thing, so I'm sticking here. Okay, it's a cylinder. Again, they're giving me the moment of inertia. Then I have a second cylinder. Oh, it's a ratio problem. You know, here's a new cylinder, different mass, different radius, different speed. What's the rotational kinetic energy? Okay, great. I love ratio problems. I'm going to use the equation for rotational kinetic energy. I have two options. I definitely want the first one because I don't want to mess with angular momentum. They gave me, like I have stuff for I and omega, so I should just do that. Okay, oh, this is great. We just got to plug in some stuff. We're going to do this equation twice, do a ratio method thing. Okay, let me put this in here so I don't have to get confused with fractions too many times. I'm going to do 1/2 mr squared for the moment of inertia. This is going to become like a 1/4, which doesn't matter because I'm going to ratio it just to make sense. And then, okay, omega squared. Okay, second cylinder. So let's do EK of the second cylinder divided by EK of the first cylinder is how I'll write it. So I'm going to do this whole equation, which is 1/4, blah, blah, blah. And the second cylinder, okay, so 1/4 times the mass. The second cylinder has a mass of 2m times r squared. So it's got a radius of 2r squared. I got to be careful with like squaring because everything gets squared. This is going to be like so much. 2 times 2 times 2 times 2 times 2. What's 2 to the 5th? I think that's what it's going to be because I also double the angular velocity. Yeah, okay. And then down here, it's a quarter again. The mass is just m. The r is just r. The omega is just omega. Cancel, cancel, cancel. But be careful because you got to square like everything in your fractions, right? So this is going to be 2 times 2 squared times 2 squared because the omega squareds canceled out. The r squareds cancel out. The m cancels out. So I got 2 times 2 squared is left times 2 squared is left. Write out more algebra steps if you want. So what? 2, 4, 8, 16, 32. I'm thinking 32 is my ratio. And remember what I'm doing. I'm solving for the rotational kinetic energy of the second cylinder. So let's solve at the end because what I just found here is the ratio. EK2 over EK1 equals 32. So EK2, just making sure I didn't ratio upside down, is 32. EK1. And they said we're just calling that rotational kinetic energy K. Why the heck not? It's C. All right, a ratio problem. Wow, my first 7 problems were feeling pretty good. Lots of mechanics, a nice little ratio thing there. Not too bad. I'm a little under 20 minutes for the first 7 questions, so I might want to pick up the pace a little bit here. Okay, a bird is sitting on a string. The rope is almost horizontal, has negligible mass. Tension in the rope. Oh, fantastic. Okay. This is like a good conceptual one. I don't think I need to solve this all the way out because I know what's going on here with tension. Here's my bird. The weight is straight down. And there's like 2 tensions, right? There's this one this way. And there's this one this way. And whenever you have angled stuff, remember the game is you got to do the whole like X piece, Y piece thing. So Forgive me for trying to write on my little tablet thing here. Even in a rough, sloppy, quick way, using a ruler on the exams is really good for this. Okay, so there's like ty and tx. The ty's is what I care about. Okay, like 2ty would have to equal the weight of the thing, right? But ty is way, 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 way smaller than t if I just look at my right triangle, right? Like this angle is really shallow. You need a really big tension for just the vertical part of it to equal half of your weight. That's really what we want. So the tension has to be really, really big. I think it's definitely got to be D bigger than W. Yeah, that's the idea. All right, the Y piece is half of your weight, but because this angle's so shallow, I am quite confident that it's going to be way bigger than W because I'm talking about tension, not just this piece of tension. Okay. Oh, we got some relativity. So spacecraft moving speed v relative to Earth. That's the regular v in my relativity equations. Passes its way. Da, da, da. Okay. The planet is a distance d from Earth according to an observer on Earth. So I want to draw what the heck is happening here. The spacecraft is moving. Okay, here's Earth. I have some other planet. Maybe it's going to Mars or something. I'll just say the planet P. The planet is a distance d from the Earth according to an observer on Earth. Okay, let's say Earth is going to be my S frame. And then we're going to say the spacecraft is going to be my S prime frame. And I want to know, I also have a spacecraft moving at some point. Okay, so the readings on the clock, we're saying it's like 0. You both agree it's 0 when it's on the Earth, right? Passing the Earth at time 0 for both people. Okay, how long does it take to get there? Well, relative to somebody on Earth, this is not so bad, I think, because we're just going to do distance equals rate times time, basically. Distance equals rate times time. So the time should just be d over v, right? That's like what we kind of expect without the weird relativity stuff. And then for this person, it's going to be the weird relativity thing. So I'm getting a time thing. So let's go here. And for my time equation, I'm going to use this guy. And I think this is good. Yeah, this seems pretty good to me because I know like t and x. In other words, I know the time and the position according to the person on Earth. So that would be, I'm thinking the best equation to use here. So let's try that. Let's do t prime equals Lorentz factor times t minus vx over c squared. Okay, by the way, I'm trying to go in order here just to make the video easy, but this would definitely be like put a star next to it, come back if you got time. At this point, I would just take like a random guess between A and B. I got it down to 50-50. That's pretty good. And if I got time at the end, I'll come back. But for the sake of this, let's solve it out. Okay. So I want to see which of these works. Okay, well, the Lorentz factor is all this junk. So t prime is going to be t minus vx over c squared over 1 minus v squared over c squared square rooted. So that's in the bottom. I'm already thinking, well, maybe not. Let's see what happens. Okay. So t prime is going to be t, which I know is d over v, right? That's like the time according to the person on Earth. So I'm putting this in for t minus v times x, and x is the distance according to an Earth person, which is d. All that over c squared. and all of that over the whole blah, 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 this thing. Okay. Yes, yes, yes. Okay, so which the heck one is it? Okay, I see they brought out a D over V, so I'm going to try to match that and pull a D out of V out of this. The D out of V, this is just the top. Okay, the first thing's going to be 1. This is interesting. I get, you're mean. Okay. If I pull D over V out of this, I get 1 for the first term, right? And like, yeesh, if I pull a V out, I get, like, it's got to be this. Yeah. To make that work, like if I multiply this back in, I'm thinking that'll give me this whole mess. So it's like this over your square root thing. Oh, that's so silly. Okay, so it's like blah, blah, blah over square root of blah, blah, blah. If we're okay with how square roots work, that turns into this. It's A. That's super mean. They want you to pick B because like this thing should be on the bottom usually. But when you do this whole craziness, you end up with 1 minus V squared over C squared. Look at that. Okay, that's a mess. This one takes forever. Again, this is like definitely, if you can narrow it down to A and B, that's pretty good. But maybe you have some time to come back and do all that math at the end. Don't spend as much time as I just spent on number 9 on like a number 9 because, oh my gosh, look at number 10. That's worth just as many points as number 9. You know what I'm saying? The internal energy of a real gas is exactly this. That's the definition of internal energy. Hey, let's move on. Okay, a gas undergoes 1 cycle of a cyclical process. The change in internal energy of the gas is what? Well, it's 0. All right. Again, if it's a cyclic process, that's again sort of the definition. Is that the internal energy is going to stay the same. No energy is coming in, no energy is going out. A working refrigerator with the door open is placed in a sealed room. The entropy of the room. This is another mean question with the working refrigerator thing. This is the key word. And it's like, okay, it's a sealed room. So here's the idea. Honestly, if it's an entropy question, probably just pick increases and move on. It's almost always going to be that. But let's picture our room with the refrigerator. And the door's open. Right? So we're picturing probably like the cold inside of a fridge, and that's what they want us to be thinking about. But why is it cold? What's it really doing? Well, it's removing heat from the air. And it's not perfectly efficient. And also the main thing, since it's a working fridge, how is it working? It's pulling electricity out of the wall, right? A fridge needs to use electricity to do this whole like pumping the heat out of the air thing. And where does that heat go? Well, it just comes out of the fridge, you know? So there's energy coming into the room. There's a net flow of energy into the room. There's electrical energy coming in, and it's a sealed room, so energy can't leave. So I have a situation where there's like a net flow of heat into the room. Delta Q is like some amount, you know, some positive amount. So delta S, the entropy of the room, increases because energy's coming in. You put heat into the room, the entropy will increase. Okay. Again, if it just says like entropy, probably the entropy increases. That's like second law of thermodynamics. Okay, black body radiation curve of an object at 600 Kelvin is shown. The intensity units are arbitrary. That's usually what they do. But they are giving me like a 1 here. So I got the height of the peak. Okay, same object at 450 Kelvin. There are 2 equations to think about here. They like to do this. The 2 equations to think about are Wien's law and the Stefan-Boltzmann law. Remember, intensity is power over area. And for the Stefan-Boltzmann law, we could say that's luminosity over area. Remember, luminosity is just a type of power. So intensity depends very, 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 very much on temperature. So if the temperature decreases, 2 things are going to happen. the intensity gets way smaller, like way smaller. And also the peak wavelength is equal to some number divided by the temperature. So the temperature decreases, the peak wavelength is going to move this way and get way shorter. So I want to pick one where that happens. Let's see. I guess that's got to be A, right? Yeah. It moved to the right. It got shorter. Kind of would think it would get way shorter, but they're doing, nah, that's fine. Yeah, that's the only one that works. It gets shorter and moves to the right. So that's got to be that. I'm just making sure the original curve is the one that's dashed. Okay, we're good. All right, 14. We got a luminosity and apparent brightness. I'm immediately like, here's my equation for apparent brightness. So I'm going to think about that. And it's another ratio problem. Oh, beautiful. All right, again, if I'm doing the paper one, I'm like highlighting this question. I might try this on the first pass if I can do this kind of quick. You can do this with the full-on ratio method. Let's see if we can do the sloppy quick ratio method. Star X, luminosity L, apparent brightness B, distance D from Earth. Star Y is the same brightness, 4 times more luminous. What's the distance? Okay, I just want to solve this for D. L over 4 pi B square root, right? Yes. Okay, so what's going to happen now? Now that I have it solved for D, I can just kind of look at my changes. It's got the same apparent brightness, but it's 4 times more luminous. How much further away is it? Well, what happens if D stays the same, but L gets 4 times bigger? It's under a square root, so if I make that 4 times bigger, it's 2 times further away. And concept-wise, it makes sense to me too. I'm going to do a quick mental check. It's 4 times more powerful, but it looks just as bright. It must be further away. And there's like a square root in this equation. So 4 is the trap answer. It's B. Let's keep going. 4 identical resistors are connected as shown. What's the resistance between P and Q? Great question. This is tricky because of how this is set up. So I'm going to measure the resistance from P to Q. So look for the connections that are happening here. Here's the idea. This is kind of hard to see, I know, but 1, 2, 3 of these resistors are in series because these aren't like really junctions. They're not, there's no connection going anywhere else. So these 3 resistors are in series, and that whole combination, because I'm connecting my meter here, that whole combination is in parallel with PQ. So it's like I got an R from P to Q, and then I got a 3R over here, and I'm going to use my total resistance equation, the 1 over R stuff. Circuits is in a weird spot. Here it is. I got to use the 1 over R thing. So the 1 over the total resistance is going to be 1 over R plus 1 over 3R. So that's 3 over 3R. So I get 4 over 3R is 1 over R total. So what, the total resistance is 3/4 R. I think we should have A for this one. That like connection is kind of funky, but that's going to be the idea. Sketch out your kind of equivalent resistors and do as many total resistance equations as you need. Okay, got some more circuit stuff. Okay, now what are we doing? We got an EMF, power, negligible internal resistance. So I don't got to use that EMF equation really. EMF is basically just voltage then. Power 16 watts dissipated here. Same material, twice as long. Okay, that's my hint to use this equation as at least part of this, because the material is all about the resistivity, and I got the length in here. So like the resistances are going to be different, and I want to know power. Okay, so I'm given these, which I'm going to treat as voltages, because EMF is really a volts thing. There's no internal resistance, so I can just treat those as my V's. I have different R's, and I want to talk about power. So I'm thinking about the power equations. I want the power equation that's got V and R in it, V squared over R. Okay. So yes, I need to see how the R's compare then. Okay, so this is like a double ratio problem. Oh, fun. Alrighty, let's do it. Rx, so X is connected to EMFE, and Y is just in terms of X. All right, so let's move this equation around, is always the good move to do when we're ratioing, or what resistance is in terms of all the other stuff. Okay, so resistance of X is just going to be like rho times whatever the length of X is over whatever the A of X is. Okay, mercifully, they're only changing the length. They're not like changing the diameter where I got to worry about area with the diameter squared or whatever. So the resistance of Y is just going to be rho times, because it's the same, 2 times the length of X over same diameter, so same area. Okay, so I think Ry is 2Rx. That's double the resistance. It's just twice as long. Everything else is the same. That's 2 times the resistance. Power is V squared over R. So I just want to compare these. The power for X is going to be E squared over, let's just call it R. And for Y, it's going to be 2E squared over 2R. So be careful, just because they both double, it's not the same because this gets squared. So I got 4E squared over 2R, which is 2 times as big as X. So double the power dissipated in X. The power dissipated in X was 16. So this has to be C, right? 32 watts. Okay, multiple ratios happening there. That one takes a while. That's okay. All right, 2 containers filled with an ideal gas, volume, temperature. Sounds like PivNert to me. I want to know the amount of substance in X over the amount of substance in Y. So I'm solving this for N. And I'm going to just ratio that twice. So I just want to do NX over NY. Okay, using PV over RT both times. So the volume of X is 4 times the volume of Y. I got my 2 temperatures. Annoying. Celsius. I have to Kelvin for PivNert. Like ratios won't work if I don't have the rate 0. So I do have to do this thing. So I add 273 to both of these, right? Which they at least gave me. Okay, they gave me the 27 so that I can do that. 273 plus 27 is 300, right? Think so. 327 plus 273 is 600, right? So it's double the temperature. Yeah, so be careful. Like it's double the temperature because I got to do the absolute temperature thing here. Okay, so I doubled the temperature and the volume is 4 times as much. So I think it's going to be 2. But I should let me ratio and make sure it's 2 and not 1/2. And let's do the whole thing for this one. Okay. Same pressure. So the pressure is the same. So let's just call it pressure P. The volume of X is 4 times the volume of Y. So I'm just going to do 4VY for the volume of X. Divided by R is just a constant. That's going to go away. And the temperature of X, I'm seeing now, let's just put in the numbers, 600. But I could also say 2T. Okay, and then I'm going to divide that by Y. The pressure of Y is also just P. The volume of Y is just VY. R is just R. The temperature here was 300. Okay, fractions, keep, change, flip. I get 4 times 300 over 600, aka 4 over 2, aka 2. That's this ratio, so NX is 2NY. Oh, I don't have to do that. I'm just solving for this ratio. The ratio this way is 2 over 1, just 2. So that'll be C. Okay, good old gas law ratio. Just be careful with Celsius versus Kelvin. Only if it's a delta T can you use Celsius. If it's just a T, it's got to be Kelvin. Okay, I'm taking too long here. I'm at like 40. Well, okay, I'm at 40 minutes. And I'm almost halfway, so this isn't terrible, but I should try to go a little quicker. An electromagnetic wave has a wavelength that's about the size of the diameter of an atom. What region of the spectrum does the wave belong to? They want me to know that that's 10 to the minus 10 meters. That's how big an atom is. You got to memorize that. I don't know why. Also, the diameter of a nucleus, 10 to the minus 15. Why, IB? Why? Okay, so what region of the spectrum is 10 to the minus 10 meters? As long as I know that piece of trivia, that's nice and easy. I just look here. That should be an X-ray. Okay, if I know it, I know it. That one's quick. Particle does simple harmonic motion. Here's the period. At time t, it's at its equilibrium position. I'm going to sketch this. I'm picturing a whole cycle as like it goes up, and then it comes down, and then it goes down, and then it comes up. What is t when the particle is its greatest distance from the equilibrium position? Like t over 4, right? Yeah, because like here, that's a quarter of a period. Then half a period is back at the equilibrium, so no. And then 3/4 of a period, it's down here. And then after a whole period, it's back at equilibrium. So sketch it out, picture for SHM, like really picture those 4 steps of the cycle. Yeah, like your 4 steps of a sine wave or whatever. And it's different if it starts at equilibrium versus if it starts at the top, you know. But you can always kind of break a period of an oscillator into 4 little chunks, which helps with a lot of these problems. Okay, standing waves. All right. Diagram 2 is a traveling wave, not a standing wave. This is going to be the in phase, not in phase thing. Yeah, okay. Points, blah, blah, blah. These are points on the string. What's the phase difference? Okay, you just got to know. For a standing wave, any 2 points in like a little loop like this, any 2 points between 2 nodes are in phase. P and Q are completely in phase. So the phase difference between P and Q is definitely 0. And then, is there a phase difference between R and S? Yes, there is, because this one's like on the way up while this is on the way down or something. Right, the 2 particles, this one goes up and down, and one next to it goes up and down, but not at all at the same time. There is a phase difference between adjacent points on a regular wave. There's not a phase difference between adjacent points on a standing wave. So it's got to be C. I don't even need to figure out why it's pi over 2. Let's just move on. Okay, mass hangs from a spring constant. What's the natural frequency? Oh, incredible. This is great. This is just using an equation. This is like kind of almost plug and chug. I just got to know where to go, which is simple harmonic motion, which is this guy. So, let's see. The natural frequency of oscillation for the system means 1 over the period. There's the period of a spring mass oscillator. So the period is 2 pi square root of m over k, which is 2 pi square root of 0.25 over 4. 2 pi 1/16. So what's that? 2 pi over 4, I guess, is the period. I think that's right. So the frequency is 1 over the period is 4 over 2 pi. So 2 divided by pi. Let's calculator this. If I do 2 divided by pi. I mean, it's got to be, yeah, B, right? That should be B if I just plug that in, yeah? So just know frequency is 1 over period. That's your equation for period of a mass on a spring. Let's keep going. Oh, single slit. Light from a monochromatic source, so 1 color of light coming to a single slit. Here's a diffraction pattern. It shows intensity with distance. Intensity remains the same. The width of the slit is increased. Okay, I'm thinking about my single slit equation. There's one equation in the data booklet. You have to know this equation is for single slit diffraction. Don't try to use it for like anything else, and don't use anything else for single slit. Gotta be this one. So that equals wavelength over B. The width of the slit is increased. That's B. B gets bigger, so theta gets smaller. So theta gets smaller, so they're going to come closer together. And then the trick is like, does the peak get any taller? Well, I think yes, because the intensity of the source remains the same. You have the same total amount of energy. But so if you have the same like total amount of light, but it's being squeezed into a smaller space, it's going to be brighter, right? It's like focusing the beam so the light gets brighter. So I think this has to be D. Where does it? Oh, the original curve is shown with a dashed line. So I got to be taller than the dashed line. It's going to be D. Okay, same amount of energy in a smaller space. It's going to be brighter. All right. Okay, diffraction grating is the equation right underneath it. Central maximum and can be observed. What can you see? Second order maximum. All right, so there's this whole deal. I don't really have to solve it all the way, but the deal with this is like how many can you see? What you do is you do the thing where you say, if this is 90 degrees, what's n? Like if I look, here's my diffraction grating, spreads out. If I look 90 degrees this way, which n do I see? I can only see the first one, so maybe n equals like 1 point something when I do this. Okay, so I need I kind of need the angle to be smaller. So what change will allow the second order maxima to be observed on the screen? Okay, let's actually do this. If I set theta equal to 90, that makes this 1. So n is like the number of maxima I can see. Right? If theta equals 90, that's like the highest n I can see. So I need to make this bigger. So that will increase the wavelength to it. No, that will make this smaller. Reduce the number of lines per unit length. Yes, that's so silly the way they say this. This will matter, this will matter. Yeah, because it's supposed to come in parallel, so it doesn't matter how far away the source is from the grating. And the distance doesn't matter. It would spread out the points you can see more, but this is an angle. So these don't matter. It's going to be D. The number of lines, it's this whole thing where the distance between the slits is like 1 over the number of lines per meter or whatever, right? This is said, this wording is terrible. Reduce the number of lines per unit length. In other words, spread the lines out more. In other words, increase D, your distance between the slits. So that's got to be D. Okay, I don't like that problem. That's stupid. Okay, 24. A solid metallic sphere is positively charged and isolated from all other charges. What's the electric potential due to the sphere? Okay, this is this thing where you got to know. You just got to know this. It's going to be A. It's this thing where like inside of a sphere, the electric field is 0 everywhere. And then all of a sudden you get outside of the sphere to the radius of the sphere, and it's like, it's the regular E equation happens. And so V looks like this because like E is, if you like, the derivative of V or something like that. Just memorize these two graphs. It's constant inside of a sphere. Okay, this is a little Kepler law kind of thing. It looks like planet in an ellipse. What quantity is decreasing for the planet? Okay, it's going this way. What quantity is decreasing? It's speeding up, right? As it gets closer, it's faster. So it's not this. It is going faster, so it has more angular momentum. The acceleration, maybe? It's one of these. The acceleration, not a perfect circle, but if it was, it'd be mv squared over r. R is decreasing. No, so the acceleration is getting bigger. Yeah, it's going to be D because of the negative thing. Pretty sure, right? Because the potential energy, the gravitational potential energy is this guy. EP is negative. Yeah, because it's negative. EP is negative. GMM over R. If R decreases, this value gets bigger, but it's negative, so that's a decrease, right? Your potential energy versus R graph is like, whoops, this way. So if R decreases, your potential energy goes down, even though the number gets bigger, because that's how negative numbers work. Okay, they're getting pretty tricky. Yeah, remember all those mechanics problems? That's why we want to spend our time on those. All right, well, how about two long parallel wires? All right, this I like. Magnetic force acting on P due to Q. We're going to increase the distance, decrease the current. It's a ratio problem. This one's not so bad if I know where to go, because there's an equation for exactly this. Super specific situation. But I need to remember where the heck it is. It's the F over L stuff. D.3? D.3. Where am I? F over L. There we go. All right. So it's this F over L thing equals this thing times the two currents over 2 pi r. Okay. Again, can I ratio without ratioing? Have I practiced these enough that I go, okay, if one of these currents decreases by half, and so this becomes half as big, this becomes 2 times bigger, I think both of those should what? Make it 2 times smaller. So overall, it's going to decrease it by 4, right? Cut this in half, double this, your total effect for the force per unit length, this whole thing is it gets 4 times smaller. Right? Do the full-on ratio if you want, but again, if you practice these enough, you can kind of look at them to be like, yeah, 4 times smaller. Okay, P is a point in a uniform electric field. And what is the direction in which the electric potential increases at P? Yeesh. Who wrote this? What is the direction in which the electric potential increases at P? So which way do you have to go for the potential to be higher? Well, I'm thinking about my potential equation, which is a little lower, which is V is K, Q over R. I mean, one way to say this is that electric field lines going from plus to minus. So I could imagine a big positive charge over here, a big negative charge over here, but they point from high to low potential. So if I'm not missing something, it's just B, right? You go from high to low potential. The field lines do. So to increase your potential, you go this way. To get towards the higher potential, the positive side of the field lines. Okay. Oh, this is the Kepler's law thing. Okay. R3T2. My favorite droid. Is a good way to remember this. The radius cubed is proportional to period squared. So the period is proportional to square root of r cubed. They really just want you to know Kepler's law here. So it's proportional to the square root of r cubed. So I'm thinking this will be D. Yeah, because you make the R 5 times greater. So yeah, D. All right, you need to memorize this. I don't know why. It's silly. That should be in the data booklet, but it's not. Okay, we're getting there. Number 29. A rectangular coil rotating. We got some flux. We got some Faraday's law or something. Rotation is perpendicular to the field. At one instant, the plane of the coil is at an angle theta to the direction of the field. Magnitude of the EMF is, well, it definitely is 0 sometimes because I just know this is where I get this like wavy EMF. Oh boy. When is the magnitude of the EMF the biggest? So when is the rate of change the biggest? Because the EMF is this whole thing, which is n times the rate of change of flux. So the EMF is the biggest when the flux is changing the most quickly. And does that happen at like 0 or 90. I think I can rule this out, and I can try to just kind of take a guess. When is the flux changing the most? But okay, the flux is BA cosine theta, right? And they're so mean, because what is theta? In this equation, theta is the angle between the normal of the plane and the field, right? And in this one, they're talking about the plane of the coil. This is so silly. Okay, so they're talking about the plane of the coil here. So this isn't the same theta in this equation. It's off by 90. The theta in the equation is this. Oh, no. It's like the angle between the normal to the plane and the field rather than the angle to the coil itself. So if the coil is like sideways, right, there's no flux. And the normal looks like this. So the angle in the equation is 90 degrees, but this angle would be 0 degrees because the IB is cruel. I would definitely, like, if you get to this point, pick B or D. They're trying to trick you. It's some stupid something. But okay, like, let's think about cosine. How does cosine work? Cosine is like, goes like this and then down and then. So cosine is changing the quickest. If you're a calculus fan, this is maybe a little, I don't know, easier. This is not easy at all, but you might know something about this, that the cosine changes the fastest, like here, right, when it's going through 0. So cosine would change the fastest at like 90 degrees. So when this angle is 90 degrees, the rate of change is the fastest. That's when this angle is 0 degrees. I am like 80% confident about that. That's an evil problem. Okay, I got a potential versus distance graph. I know one thing immediately is the whole, this is like a graph to memorize, that the gradient of this graph is field strength. Let's see if that does anything for me. What's the escape speed from the surface of the planet? The surface of the planet is your one radius of the planet away from the planet. So this is the point I care about. I could use this graph to find the field strength at that point. Will this help me with my escape speed? Well, kind of. I can do some trickery. This is also pretty mean. This is like a put a star next to it and try to do some math later, because there's going to be some math here. So let's do it. All right, there's maybe a quicker way to do this, but this is the way I'm going to do it. Is G m over r squared. Okay, the escape is square root of 2gm over r. So can I do something with that? Okay, this is kind of weird. You might have a better math way to do this. I don't know. All right, gm over r, I'm thinking is the same thing as g times r. Yes, because g is gm over r squared. If I multiply that by r, I get this. So a very funky way to say this is 2g little r. So if I use the graph, I can find little g, and then I could plug it in here. But I don't know if that helps me, because blah, blah, blah. Oh, I see. This is going to be less crazy than I'm thinking. Because I don't know what the radius of the planet is, so... Well, okay. That'll work. That'll work. I think there's a quicker way to do it, which is Vg is negative gm over r. So like that's pretty similar to what's going on here, right? Gm over r. So the escape speed is like square root of 2 times Vg. With some kind of weird negative, but who cares? The V, yeah, it's fine. The Vg is negative itself. So it's like 2 times negative Vg is what this is. Yeah. Okay, this is better. So we would just plug in Vg at the surface of the planet then. The Vg at the surface of the planet is 5 times 10 to the 6. So the escape speed formula, if I finagle it, is square root of 2 times negative 5 times 10 to the 6. Watch out for this thing. So like 10 times 10 to the 6. So we want to just do square root of 10, which is like 3 something. So what is this going to be? C, I betcha. Yeah, we should get like 3.16 times 10 to the 3 is what I should get. So that's C. Yeah, okay. Another ridiculous problem that takes a long time and you got to do some math, jujitsu. This would be a like save it for later. See if you got time to try some math and just pick a letter of the day. I would say, okay, charge rod, metal sphere, insulator, conductor stuff. I think charge rod, neutral metal sphere without touching it. When the sphere is grounded, there's a current for a short time from the sphere to the ground. The connection is then removed. What's the charge on the rod and charge induced to the sphere? Okay, without touching it tells me there's going to be no transfer of charge. So whatever, direction of conventional current. Okay. All right. So whatever charge is on the rod is going to stay on the rod. It would have to touch the sphere. We're assuming that it's not so charged. It's going to like arc. Okay. So conventional current, positive charge is flowing this way, which means the sphere ends up with a negative charge. Okay. And like, why did that happen? The positive charges must have been repelled, which means the charged rod must be positive. Yeah, that's my thought process. If the conventional current is going this way, that means positive charges are flowing this way, like basically. And the charge rod must be positive because of that. So which one of these is that? The charge on the rod is positive. Charge induced on the sphere is negative. C. Okay, 32. A positive point charge of 1 microcoulomb. Two charges separated by some distance. Then we put an electron over here. Force on the electron is 0. What's Q? Okay. First, there's 2 positives, 2 negatives. Let's do a little paper one strategy. Let's do some elimination. The positive charge is going to, I'm going to call this like A and B or something. The positive charge is going to attract the electron. This charge must be repelling the electron, so it must be negative, right? So get rid of those. And it's 2 times further away. There's an r squared. My hunch is A because of that stuff. Yeah, because the force is Q1, Q2 over r squared. And I need these 2 forces to balance, right? Those 2 forces on the electron must be equal. So the first one is like K. Okay, let me do it this way. So the force from A is going to be K times Q1 is the charge of an electron, which is E, times Q2 is 1 microcoulomb, divided by the R is D squared, right? Okay, now that's equal to the force from the second one. So we're going to do KQQ over R squared again with the new numbers K. The first charge is still the charge of the electron. The second charge, though, is my mystery charge Q. And the distance now is 2D, but that whole thing is squared. So I'm going to solve for Q in terms of Whatever else I got, everything's going to cancel out. I got a 2 squared. That's going to be a 4. I'm going to get Q equals 4 times a microcoulomb. I know it's negative because this equation doesn't tell me about plus minus. It just tells me the size. It's got to be negative because if this is positive, that's how it's going to, work out. All right, sequence of evolution. 2 solar masses. That's a low mass star. It's going to be a white dwarf. Get rid of that. Get rid of that. Only big star is supernova. It's B. I studied it. I memorized it. That's it. Memorize it. That's what happens with a low mass star. Okay, I hate this question. They've done this question before. It shows the emission spectrum of an atom. Which energy levels could provide this spectrum? Oy, oy, oy. Well, it's like you got 2 lines close together over here, 2 lines close together over here. The trick is the different wavelengths correspond to the different possible transitions you can make, which are like all of these. It's gonna be not B. Those are all even. Like I'm thinking there are 2 really close wavelengths over here. It's like this thing where the energy of a photon is like the energy difference in your levels here. So 2 energy differences have to be really similar here on the low wavelength end, and 2 energy differences have to be really similar here on the high wavelength end. And then there's 2, there's like this one and this one. I think it's got to be A because that's the like it's yeah, you have 2 sets of almost like same energy, right? These two lines mean like about the same amount of energy. These 2 lines mean about the same amount of energy. And these lines would be the most energy because it's the wavelength thing. So it's like your biggest transition. So yeah, it's like this one and this one are basically the same length. And I'm thinking that's going to be these 2 lines. But then you have the like still a lot, but not as big as the other 2. That's going to be like this line. Then you have the biggest one, the biggest transition is like this. That's going to be that line. And then, okay, yeah, then the other 2 like little weird ones, like this guy and this guy are also really similar in size, but a little bit of energy, so real long wavelength. So it's going to be these 2. All right, it's like trying to draw out the different possible transitions and how long the arrows are, and how long the arrows are is how much energy the photon has. I don't like that question. That's like a lot. Okay, 35. Scattering of a photon. This is Compton scattering. It's new, so they're gonna ask you about Compton scattering, which I bet you will be something quite like this. Because what's the fraction of the incident energy that gets transferred to the electron? Okay. Fraction of the energy. Okay, well, the photon energy is h times f. Oh, okay. This is kind of tricky. Photon energy is h times f, which is also hc over wavelength, I think is the version I want because this is all wavelength stuff. So how much, a fraction, silly. How much, how much energy gets transferred is going to be how much energy the photon loses. So like I got energy at the end, energy at the beginning. That's how much energy gets transferred to the electron, right? And then I would divide by the fraction of the incident photon energy. I would divide by the energy before it did its thing. Okay, I'm thinking I want to flip this because the energy of the like original photon is bigger than the energy of the scattered photon. Like this is less. And so I don't honestly know if this is going to matter, but to do this the official way, like the energy gained by the electron is like the difference here. That's a positive amount. And I want to divide by the fraction of the incident photon energy. So the energy of the original photon is what I want to divide by. So let's see what happens, because there's going to be weird fraction stuff here. It's going to be this minus this over the original. Right. Yes. And get rid of HC, right? Can't I? Okay, I can get rid of the HC, which is this. I think it must not be C, because like that would be if I didn't do the 1 over thing. That seems like the trap answer. But this is just a math problem. Yeah, this is just like a doing math with fractions things. So, okay, I guess I'm going to keep change flip. So let's do 1 over wavelength minus 1 over new wavelength times this, because I'm dividing by that fraction. So I can distribute this in. What is happening? Okay, minus this over this. That's 1 minus this over this prime. Which one? That's D, right? Because common denominator. So it's D. That's like a harder math problem than it is a physics problem. I don't like that. But that's there you go. D is the answer because of all fraction nonsense. Another one where don't spend a ton of time on that math. You can narrow down to C or D and flip a coin. That's pretty good. Okay, 3 statements about a nuclear fission reactor are 1, 2, 3. Which statements about the reactor are correct? Okay, let's see. The heat exchanger transfers energy from the fuel rods to the moderator. Okay, the control rods must be good absorbers of neutrons. Yes, because I want them to I want them to like absorb the neutrons to control the reaction. The moderator must slow neutrons down. Yes, that's the job of the moderator so that they're easier to be absorbed. I don't think A. The heat exchanger transfers energy from the fuel rods to the moderator. No, we want to transfer it to like water that's not in the reactor. You don't want to heat up the water in the reactor. You're heating up water outside the reactor to like boil it more or less and make steam and turn a turbine. So I'm thinking this is going to be C. A sounds kind of close, but you don't want to do that. Okay. HR diagram. 2 stars, X and Y. What's radius of X over radius of Y? With like they're 2 different temperatures. Okay, so they're 2 different temperatures. They're at the same luminosity. So I'm thinking it's gonna be this guy. So I want to know, okay, radius ratio. Let's solve for A. It would be L over this. A is like 4 pi r squared. So R is square root of luminosity and junk. No, I need the temperature. I lied. I was trying to be lazy. Okay, I need the temperature. So the luminosity is the same, but the temperatures are different. So it's like L over 4 pi, this T to the 4th, right? Okay. Fraction fun. What's radius of x over radius of y? Well, let's first do our elimination thing, because 2 are smaller, 2 are bigger. So what would make sense if x is equally luminous but way hotter, it must be way smaller, right? If it's way hotter, if they're the same size, the hotter one would be much, much more powerful. So it must be smaller. So it's got to be one of these two. And I think that makes sense because the temperature of x is 4 times the temperature of y. So I'm thinking, what happens if I make t 4 times bigger? Well, if I make t 4 times bigger, it's like a 4th power in the denominator, and I square root it. Okay, if I do this, then I'm going to end up with square root of 1 over 4t to the 4th. Or just 1 over 4 to the 4th. The t's will go away. You can do this, right? That's 1 over 4 squared, so 1 over 16. Okay, so ratio-wise, because I 4th power it and square root it, that's like squaring it. So I'm squaring 4 times more, which is 16, and I know it's smaller, so it's got to be A. Okay, home stretch, here we go. Energy in the nth level of a hydrogen atom. Well, I know there's an equation for this. What's the frequency of the photon emitted in the transition from n equals 4 to n equals 2? Okay. Well, the frequency of a photon is E equals hf, and E is the difference in energy levels. So I got to do the difference in the n equals 4 and n equals 2 levels. And I would multiply that by, no, for frequency, I'm going to divide by h then. So, okay, the 4th energy level, they're just giving me this instead of the 13.6 or whatever. Okay, so n equals 4, it's just E over 4 squared. N equals 2 is this over this. They really are loving the fraction math for this one. So what? So let's get ourselves a common denominator here. Like this. Yes, so that's like, I guess I subtracted the wrong way. That's okay. This is going to be like 3 over 16. Yeah, so I just take the difference. That's how much energy the photon has. That's E. And I'm just going to divide by H. So I think we should have B here. Okay. Monochromatic light, surface of a metal. That's the photoelectric effect. Stopping voltage for this light is V1. Frequency is changed to F2. What's the new stopping voltage? What the heck? What? They're getting weird here. They get pretty weird around the end. All right, so the frequency is we're going to change it. Now we have a new stopping voltage. How does the stopping voltage relate to the frequency? E max equals HF minus work function. Well, remember the deal. The stopping voltage is to stop the electrons. The stopping voltage, you multiply by the elementary charge, which I see E's in the answer, so let's do it right and say that's E. That's how you figure out how fast they were going. The whole point of the stopping voltage is to say, how many volts does it take to stop this electron, because a volt's a joule per coulomb. And so I can roundabout figure out how many joules of energy the electrons have if I multiply joules per coulomb by coulombs, right? I'm just doing work equals QV, the classic. So you want to know the stopping voltage. The whole deal is you multiply it by the elementary charge to get this max kinetic energy thing. So now I can do whatever the heck they want me to do here. I'm going to change the frequency to F2. Now it's the new voltage. So, okay, there's so much stupid fraction stuff happening here. Okay, the stopping voltage is HF minus work function all over elementary charge. I'm going to do that twice and then divide by F minus F. Why, IB? Why do you do these things? Okay, let's do it. So V2 is going to be HF2 minus the work function, which is just whatever, over E. Okay, V1 is going to be HF1 minus work function over E. And divide all of that by F2 minus F1. They are basically testing if you know how fractions work, which is very silly. So what happens here? What happens? All right, I see a bunch of H over E things, so we can take out the H over E. I hope there's like an easier way to do this than I'm seeing, because this is just silliness. H over E for the first one is going to be then F minus no, this is not thing, is it? Okay, okay, this is just the top, by the way. It's all this over this. So minus this plus this, those go away. Oh. Okay, well, this is fun math, I guess, but this is not a little ridiculous for paper one. It's just going to be F2 minus F1 here over F2 minus F1. Cancel, cancel. It's B. Is the answer to this one. Yikers. All right, and lastly, an alpha particle moves towards the center. Distance of closest approach. Hey, I studied this. I memorized this. Kinetic energy. It starts with all kinetic energy, and then it turns into all potential energy, all electric potential energy, which is this guy, K, Q1, Q2 over R squared. Nope, R. And all right, I don't need this whole thing because this is the kinetic energy. So that's that. I'm going to solve for R. So let me do this first. I see a mega in there, so I'm going to have to deal with that. They are really enjoying you having a calculator for the paper one now. They're going to make you do a whole bunch of calculator nonsense on this last one. It's this many electron volts. I got to be careful of that. Equals all of this stuff. So R is K, Q1, Q2 over that many EVs. Okay. All right, so what are the charges? K times Q1 is an alpha particle, so its charge is 2 times the elementary charge. Then I got 79 times the elementary charge. All of that over 5.5 times 10 to the 6 EVs. Okay, remember, be careful. We're going to need to make this joules. Let me keep this here for a second. You're going to be able to cancel like one of these E's if you're fancy, but I don't want to mess with doing too much at once. All right, I got E and E here. So like, here's the idea, right? You would square this, but then I'm going to divide by 5.56. Now 5.5 times 10 to the 6. And I got to multiply by that same amount to turn an electron volt into a joule. So like times 1.6 times 10 to the minus 19. Like that's how many joules. So I can calculator simplify at least a little bit here and be like, okay, well, that goes away, that goes away. All right, so I'm going to calculator here now. K is in the front of our data book, I write 8.9. 8.99, 10 to the 9. This thing, so we're going to put that in for K. And calculator our way to success, hopefully. Let's see what we get. 8.99 times 2 times 79 times 1 elementary charge divided by 5.5 million. And I get B. B for that one. Okay. Whoa, boy. All right. So as you can see, the paper one gets a lot more fun towards the end. The IB is especially getting real weird with this one. There's a ton of weird fraction stuff in here, more so than I would say is usual. But there's going to be some real tricky ones that take a lot of math, and there's going to be some real quick ones. So the strategy you want to do is to page through the paper one before you really do much solving, or at least as you page through the ones you see that you know you can do immediately, do those first. Do the ones that you can do quickly, and the ones that are going to take you like 5 minutes to math all the way out, save them for later. Remember, also, don't lose your time for the paper 1B. The paper 1B, similar, there's a lot of like very doable marks on there. Like you might get a point for just drawing a trend line that crosses all the error bars, you know, or like knowing the uncertainty rules. So between the paper 1 and paper 1A, paper 1B and paper 1A, make sure you like pick up the easy points first. Spend most of your time on the easiest stuff, right? It is super easy to spend most of your time on the hard stuff, but you really want to spend most of your time where you can get the most points. Because again, like all of the math that it took you to solve some of those later crazy fraction ones, like this problem is worth exactly as many points as, you know, one of these stupid fraction problems. Like that problem is worth just as much as this problem, and is just as much as like all of these weird problems. Yeah, so spend your time up here. Make sure you get the points on the ones you can definitely get the points on. It's a time management game as much as anything else, because it's a stupid standardized test is what it is at the end of the day. So don't sweat it so much. Give it your best shot. Spend your time wisely. All right, good luck and have fun.